Hi guys, we are welcome once again to the Smart Way lectures for the Science Ambassador series. This is a series of lectures we are running on all the areas in science, and today we are here with you to continue on thermochemistry, that is also called energy and energy changes. In this lecture we are going to look at the standard enthalpy of neutralization. In our last lecture we looked at the standard enthalpy of combustion. We said that the standard enthalpy of combustion is the amount of energy liberated to the surrounding when 1 mole of a substance is burned in excess oxygen under standard conditions. We're able to do some calculations and do some practical measurements. Now today we are going to look at the standard enthalpy of neutralization. Now when it says standard enthalpy of neutralization, what do we mean? It all boils down to understanding neutralization. When it says neutralization, it's simple. It is a reaction between an acid and a base to produce salt and water. Neutralization is a reaction between an acid and base to produce salt and water. Now this typically happens to people who have stomach pain and have indigestion or constipation. Now this is usually as a result of high accumulation of acid, hydrochloric acid in our stomach. And in that process, if you want to clear the acid, we neutralize the acid by adding the base. And the base we add to our stomach, it comes in the form of a tablet. So the base usually we add to our stomach is called the milk of magnesia. It's called the milk of magnesia. The milk of magnesia. And the chemical formula is magnesium hydroxide. It's magnesium hydroxide. So this is added to our tablet, and then when we take it to our stomach, it reacts with the what? With the base. It reacts with the acid, and then clearing the acid out, and then produce what we call salt and water. The reaction between the base and then the acid, or the acid and the base to produce salt and water, is what we call the neutralization reaction. Now, as we said that every reaction is brought about as a result of some amount of energy required in the reaction. And so therefore it means that even when we add the milk of magnesia to the acid in our stomach, there is some amount of energy change in the reaction. The energy change during the process is what we call the enthalpy of neutralization. Enthalpy is simply energy, and so it's called enthalpy of neutralization. Good. Very, very simple. Now, but because at various conditions energy changes, we perform this experiment under standard conditions. For standard conditions, we perform them under room temperature conditions. That is 298 Kelvin and then 1 atm. Now, if you are using concentration, then it means that all concentrations must be what? 1 molar. And so, because we are going to use concentrations of acid and base, it means that our standard quantities must be 1 molar acid and 1 molar base. And so when you say standard enthalpy of neutralization, we are talking about the energy change or liberated when 1 mole of an acid reacts with 1 mole of a base. The energy change when 1 mole of an acid reacts with what? 1 mole of a base. Now, this reaction usually produces what? Salt and water. This reaction produces salt and water. So you can see from here that I have added 1 mole of acid to this 1 mole of base. This whole quantity is 1 mole of acid, and this whole quantity is 1 mole of base. When I bring them together, the two will all be transformed to the salt solution. That is what will be formed here. The energy required to form this or liberated during the process is what we call the standard enthalpy of neutralization. This reaction must take place at standard conditions. The reaction must take place at standard conditions. So quickly, let's look at examples of that. So that we can better understand them. Let me take you through the first one. Now, I have an acid, that is ACl. Now, if I add it to a base, we are saying that we will get salt and water. So we are going to get the first salt that will come out is sodium hydroxide, that is sodium chloride, and then we are going to get water. Good. So, but you see, the acid comes in a form, it is in water, so it is normally aqueous. We describe those solutions as aqueous. So everything will now be in water. So we are going to write aqueous, but water will be in the liquid form. Okay, we cannot write aqueous for water. Okay, And so this solution, this acid solution is in water, so it is aqueous. And then this base solution is water, so it's aqueous. We are saying that when you add 1 mole, okay, when you add 1 mole of an acid to 1 mole of a base, when you add 1 mole of an acid, so this is the base over here now, and then this is the what? The acid. So we are saying that if you add 1 mole of an acid to a 1 mole of base, you are going to get what we call the what? The salt and water. Now the energy required or liberated during the process of adding the 1 molar acid to 1 molar what? Base is what we call the standard enthalpy of neutralization. So this is very, very simple. So this is what we mean by standard enthalpy. The enthalpy chain, that is the standard enthalpy chain, okay, for neutralizing the acid. For neutralizing the acid, okay, that is the 1 mole of the acid is equal to, we have gotten a value for it, which is 57.5. Okay, that is kilojoules per mole. That is kilojoules per mole. Kilojoules per mole. So the change in the enthalpy that will occur, that is the energy that will be liberated or that will be required to completely neutralize the ACl, okay, to form the salt solution, is what we call the standard enthalpy of neutralization. So once again, standard enthalpy of neutralization is the amount of energy liberated or required or changed when 1 mole acid is reacted with 1 mole base, okay, at standard conditions. And this is the value that we are talking about. This is the value when you add hydrochloric acid to sodium hydroxide, the energy that will require to completely neutralize the two solutions, the two acid and base, is negative 57.5. We will be measuring this energy very, very soon. So this is the first one. Now again, let me give you another example. So this is the first one. Let me give you another example. Let me take hydrogen nitrate. That is also one acid. Hydrogen nitrate. So I have hydrogen nitrate here, which comes in the form of aqueous, and then let me add it to potassium hydroxide. Let me add it to potassium hydroxide, which is also in aqueous. It's in water, so let me write it aqueous. Now when I add this, I'm going to get what? Now when I add this, I'm going to get potassium. I'm going to get potassium what? Nitrate. So I'm going to get potassium nitrate. Always the first element goes to what? Combine with the second element or the radical. The first element here, that's the first element of either the first or the second compound, goes to combine with the second what? Element or the second radical. So nitrate is a radical, so potassium goes to combine with this whole radical here. So we get the first one as the salt. And then the last one, say salt and water, so the last one is what? Water that will come out. But remember that we are performing the reaction in what? In water. And so this salt will also be in water, so we write aqueous, and then water will be what? A liquid. So there is an amount of energy that we require when I add this acid. When I add 1 mole acid of this, when I add 1 mole acid, okay, that is when I add 1 mole acid, okay, plus 1 mole of what? Of base. So when I add 1 mole of acid plus 1 mole of base, the energy change during the process of adding 1 mole acid of hydrogen nitrate to 1 mole base of what? Potassium hydroxide is what we call the what? Standard enthalpy of neutralization. We have also found out that the value also remains the same. So the value, the standard enthalpy, okay, that is the standard enthalpy. This symbol represents standard, and N represents what? Neutralization. So the standard enthalpy of neutralizing this acid, okay, of this acid, okay, we've also found out that the value also remains the same. We also found out that the value also remains the same as this one. So the value this and this are the same. Let's give another example. If I add this one, let me take another example like hydrogen bromide. that is an acid, 1 mole of the acid, and let me add it to sodium hydroxide. Let me add it to sodium hydroxide. Now remember that the acid is in the water, so aqueous. The base also in water, so aqueous. When I bring them together, the first element goes to combine with the second element. The first combine with the second. So we are going to get this combined with Br, sodium Br plus what? Plus water. Plus water. So plus water. Now this is in a liquid form, and then sodium bromide will exist in the water, so it will be aqueous. And base also be aqueous, that will also be aqueous. Now when 1 mole acid, okay, is combined with 1 mole base, when 1 mole acid is combined with what? 1 mole base, 1 mole base. Now the amount of energy required or changed or even liberated when 1 mole acid reacts with 1 mole base, okay, is under standard condition. Under standard condition is what we call the standard enthalpy of neutralization. We have also found out that the standard enthalpy value for neutralizing the hydrogen bromide, okay, hydrogen bromide, is also close to the same value. That is 57.5. Okay, 57.5. So this is what we call standard enthalpy of neutralization. When 1 mole acid reacts with 1 mole base, the energy change during the process is called that. Now, how do we measure the energy change? I have given you how to do that. So let's quickly look at how we do the energy. Okay, so the enthalpy change for every reaction, once again, is giving us the summation of all the change in the product. The summation of all the change in the product, that is the standard. Okay, the summation of all the change in the product, the summation of all the change in the product minus the summation of all the change in the what? In the reactant. So this is the value for all enthalpy change, irrespective of the type of what? The enthalpy, if it is neutralization or combustion or hydration, this is the value. Because we are dealing with a reaction called neutralization, the enthalpy change becomes the standard enthalpy of neutralization. So standard enthalpy of neutralization. By this time we are neutralizing what? The first case, we neutralize what? 1 mole acid. So we neutralize 1 mole acid. And so therefore, what are we going to do? We will subtract the sum of all products from the sum of all reactants. So we will write the reactant, we write the product here. So that is, we write this one, the standard enthalpy of formation. I told you that the subtractions are done in terms of formation. Okay, so formation of this, the standard enthalpy of formation of sodium chloride, okay, the standard enthalpy of formation of sodium chloride, okay, plus the standard enthalpy of formation of what? Of water. Standard enthalpy of formation of water. Okay, standard enthalpy of formation of water. Now all minus the standard enthalpy of formation of the reactant. And how many reactants we have? We have 2 reactants, 2 products and 2 reactants. So we are going to also take the value there. So we are going to get the standard enthalpy of formation of the first reactant, which is what? This is this. So we are going to get this. I'm going to get that. And then plus the standard enthalpy of formation of what? Of the acid, that is 1 mole, this one. So the standard enthalpy of what? Of formation of this, of that. So that is the energy required. So this value that we have said, okay, this value that we have just talked about is found by subtracting the sum of the formation of all reactants away from the product. You sum all formation of what? Reactants, the sum of formation of all reactant away from the sum of formation of all product. So then when you do the subtraction, these are the values we are going to get. So first one, you are going to do this subtraction and you are going to get this value. Second one, you are also going to do the same subtraction using the specific reactant and product. We are also going to get what? The same value. Now, it is very important to also know that the definition standard enthalpy chain can also be defined in terms of the quantity of what water that is produced. The standard enthalpy of neutralization can also be defined in terms of the quantity of water that is going to be produced. So when you look at these three reactions, you realize that the three reactions involve the adding strong acid and to strong base. We've observed that anytime you add 1 mole of acid to 1 mole of base, there is a quantity of water that is generated. So you can see from all these reactions that the quantity of water produced is 1 mole, and here's also 1 mole, and here's also 1 mole. The equation is balanced, but the quantity of water generated, okay, from the process is 1 mole here, 1 mole here, 1 mole here. So we can also define standard enthalpy of neutralization with respect to the quantity of water that is produced. And so we define standard enthalpy of neutralization in terms of formation of that, okay, in terms of formation of the quantity of water. So this is how we can also define the standard enthalpy of neutralization. That is, we are defining it with respect to the quantity of water produced in each case, okay. Here I said that the quantity of water produced here is 1, and here is also 1, and here is also. Now we can also define standard enthalpy of neutralization as the amount of energy liberated when 1 mole of water, here is formed from the H plus ion, okay, it's formed from H plus ion from an acid and OH minus from a base. H plus ion from an acid and OH minus from a base. We can also define it as the amount of energy liberated when 1 mole of water is formed from H plus ion from an acid and OH minus from a base. Okay, good. So, and that is the value. So let's write it quickly. Let's quickly write that one here. So in the first case, let's write that one. We are going to get the amount of energy liberated when 1 mole of water is formed from H plus ion from an acid and OH minus from from a base. So from a base. So we have from a base. So here what are we going to get? We are going to get 1 mole of of water. So you can see from the reaction that when 1 mole of a strong acid reacted with 1 mole of a strong base, 1 mole of water was produced in all the three reactions. And so we can define standard enthalpy of neutralization as the amount of energy liberated when 1 mole of water is formed from the H plus ion, okay, from an acid and the OH minus from a base. And so this is what I have written over here, okay. We can also define it like that. Now this definition is because anytime a strong acid reacts with a strong base, there is a complete dissociation of the acid. So anytime acid reacts with a strong base, okay, anytime a strong acid reacts with a strong base, there is a complete dissociation. That is, the acid breaks down completely and the base also breaks down completely. And so they form a completely neutral solution, where the solution will neither be acid nor base. So this definition is because why? When 1 mole acid, then when 1 mole strong acid reacts with 1 mole strong base, the strong acid completely dissociates, okay, to form a completely neutral solution. And the energy that is formed during the process is the same as the energy that is formed when 1 mole of water is formed from the H plus ions and then the OH minus, okay. So the energy value for this is also the same. So this is also having the same, the standard enthalpy of neutralization for this. So the standard enthalpy for neutralization, okay, here is the same as the standard enthalpy, is the same as what? Is the same as this negative 57.5. Okay, so that is kilojoules per mole. That is kilojoules per mole. That's kilojoules per mole. So this one, we can say this one is a formation reaction. This is aqueous. The acid must be in water, so it's aqueous. And here is also aqueous. Then water is a liquid. Have you gotten that? So you can see that this is a formation reaction. And in the formation reaction, it is the same as that of adding what? 1 mole of pure acid to 1 mole of a pure base. Good. In this case, the enthalpy of neutralization, okay, of the H plus ion is the same as the enthalpy of formation, that is the standard enthalpy of formation of water from 8 ions, okay, from 8 ions. So the values here are the same. So we can also define it that. Now, there's one thing that I want you to know before you go, okay? Now, whenever a strong acid reacts with a strong base, there's a complete dissociation of what? Of molecules, and so the amount of energy released are always what? The same. So you can say that when a strong ACl reacts with a strong sodium hydroxide, there's a complete dissociation of each of the molecules. So they resulted in what? This value. This is also strong acid, strong base, so they resulted in the same thing, okay? But anytime you add what? A weak acid to a strong base, or vice versa, the value that you are going to get is always different. So for instance, if I have if I have a weak acid like this, that is ethanoic acid. If I have a weak acid like ethanoic acid like this, now if I add it to a base, that is a strong base, I will get what we call the sodium ethanoate. I'll get what's called the sodium ethanoate. The sodium ethanoate. Sodium ethanoate, that is the salt plus what? Plus water. Now, we are saying that this is a weak acid. This is a weak acid. And this is a what? A strong what? Base. So this is a strong base. And this is what? A weak what? Acid. Now, we are saying that anytime you add a weak acid to a strong base, the value that you are going to is not the same as this one. Okay? So, why? Why is it happening? Because we are saying that when a strong acid reacts with a strong base, there's a complete dissociation of what? Molecules. And so the energy liberated during the process is what? Is high. So 57.5 is the energy liberated to the surrounding whilst forming the what? 1 mole of water from this case. But here, for weak acid there is what we call partial dissociation. Not all the molecules get to break down naturally. For weak acid, when you add weak acid to strong base, not all the weak acid break down naturally. So some of the weak acid remains in the solution, okay? That is unionized, okay? But what happens? Because the reaction must go on, the reaction normally absorbs energy into the system. Instead of liberating the energy for us to measure, okay, it's rather take up energy from the system to make sure that the reaction comes to completion, which tends to lower the heat that is what? The overall heat that is what? Given to or liberated to the surrounding. So there's what we call some level of endothermic reaction in the overall what? Reaction, okay? So this is what it is. Again, when you also add a strong acid, okay, like ACl to a weak base, let's take an example of a weak base like aluminium hydroxide. Aluminium hydroxide is a weak base. The group 4 and group 5 hydroxides are weak base, okay? So when you add a strong acid to this weak base, the aluminium hydroxide will not completely break down, okay, naturally in the process, and so there is some amount of energy that is absorbed from the surrounding, which tend to lower the overall heat that's given off during the process, okay? So that is also another example. And the weakest one is when a weak acid reacts with a weak base. That case here, the amount of energy liberated to the surrounding is the smallest, because each of these reactions will absorb energy into the system, lowering the overall energy liberated from the reaction, okay? So this is what we call the standard enthalpy of neutralization. In our next video, we'll be looking at how to experimentally determine this value.